at the end, in the last session, I think we ended here. So basically we use microwave, and then this is comparison between microwave and conventional heating. Okay, so if you look at the diagram, I only tell you the conclusion. Okay, because it's very difficult to interpret very detail and without the spending a lot of time. So this basically the graph shows the MW means the microwave heating. If you look at here, I'm gonna circle this. So the microwave. Okay, so my microwave heating, MW heating, microwave heating compared with conventional heating. So to basically at 550 degrees C under microwave, and then we already reached the beginning 70% conversion, and then a level of the conversion level of somewhere around the 50%. Now, if you look at the conventional heating, which is thermally heated, and then there's a 600 degrees C, and then it's only reached a 50% conversion. Okay, so the basic, and also the conversion actually the decrease, and with increase of the flow rate. But I mean, basically, these two graphs are compared under the similar flow rate, 120 120 the cc per minute, 30 and 60. So what's the differences between the microwave heating? Okay, so flow rate means you know how fast you flow the molecule into the reactor. Okay, so the and then if you change the flow rate, you find out microwave conversion doesn't decrease, but if you increase the flow rate, and then the conventional heating the decrease. So I don't want to ask question, because if I keep on asking question, there's no end. So the reason being that microwave heating can sustain it's basically the heat transfer rate is much faster. Okay, so just remember that flow rate doesn't affect um uh, the conversion, but in the conventional heating it does. So the reason being that if you look at this cartoon, so the microwave heating, the heat from direct inside out, the heat transfer is very fast. So that means whenever the reaction need heat, microwave can sustain that reaction. But external conventional heating is from external to internal. So when internal temperature need 600 degrees C, external heating may not reach there because the heat transfer is limited. So microwave is rapid heating, and then that's one of advantage. This is the reason that heat transfer is very important in the pyrolysis, because you need to deliver the heat whenever the catalyst is needed. Okay. So let me see where's my graph here. All right. So yeah, I don't want to interpret this side. I just want to show you microwave has a lot of advantage compared to conventional heating. Right. This is another angle to look at the microwave heating versus conventional heating. So under the under the similar reaction condition, so microwave basically is start from, I'm talking about production rate per hour. It's 25 mole per hour, whereas the conventional is only the 15 mole per hour. It's exactly the same testing condition, 550 degrees C, and the same flow rate. We compare the same condition. So regardless, in terms of heat transfer and also productivity, microwave is much higher, much better than conventional, largely because of the heat transfer and also the selective heating. Okay, all right. So I want to quickly go through this, because unless you are working in this field, it's very difficult to to interpret this. So maybe what else I should say? This is another angle to look at the microwave to the conventional heating. So if you're familiar, let me draw the picture. Give me 1 second. I'm gonna show you. Okay. I'm going to stop sharing. Basically, the microwave. You may be wondering why microwave is so effective. They actually change the activation energy. I'm gonna show you a cartoon. Okay. So can can you see the what I'm showing here?
Yes, sir.
All right. So essentially, this graph basically shows. Remember we talked about activation energy, all right? So you have reactant, you have product. Without catalyst, and then you basically you have to cross this mountain activation energy. With the catalyst, you reduce the activation energy. That's why the catalytic reaction is so important. Now with the microwave, we further reduce this activation energy. So there's a way to calculate activation energy. This is how high is activation energy. So this is the this is a theory behind it. So activation energy is the dictate, how easy, how difficult to the wrong direction. Okay. So now we basically obtain the laboratory data under microwave, and you run the different temperature, you obtain the activation energy. Microwave is 24.5 kilojoule per mole, and then thermal is 45.5. So that means if I use this cartoon to compare, so this green line is similar to microwave, and then the red line is more like a thermal. So that means with the microwave, we basically cut the activation energy by half. That means it's easy to run the microwave reaction, because the microwave really induce the activation of the molecule. Okay, so there are a lot of the kinetic study, kinetic modeling work behind this. And then if you want, I can send you a paper published in Applied Catalysis B. So, but this is the different angle to look at the effect of the microwave in driving the methane pyrolysis. Okay. All right. So based on all this data, we have done the techno-economic analysis, and then if you're familiar with ammonia synthesis, we spend almost 2 days to discuss about techno-economic analysis on ammonia synthesis. Same thing here, techno-economic analysis on the hydrogen production using pyrolysis. So this is the assumption we make, not assumption, the data, how much it costs the catalyst, and how much it costs the raw material, and how much hydrogen we can sell. So all these are the data we need to factor into the process simulation, and then end with the techno-economic analysis. And then when you do the techno-economic analysis, you need a process simulation. All right, you have to draw different unit operation, and then compare with the baseline, which is commercial case. There's a commercial case for the methane pyrolysis, and we want to compare the commercial process with the microwave pyrolysis. So the base case and also the microwave case, it's very similar to what I present to you in ammonia synthesis. Okay, I'm only going to show you the result. So here's the result. It depends on the scale. Okay, if you have a small scale, the minimum carbon selling price. Remember, we use the word minimum ammonia selling price. Here's the minimum carbon selling price, and then it's pretty high. You need to sell carbon at $8 in order to make money. Okay, remember the methane pyrolysis, we produce hydrogen and carbon. So the economic analysis, and then by the assigning a hydrogen price, we want to know what's the price of the carbon we need to sell in order to make money or break even. Okay, so that's the techno economic analysis the result. Okay, so it's cartoon really tell you small scale, because you do not have the economy of scale, you have to sell your carbon at a very high price, $8. Today, give or take, carbon black or the many carbon is sold much less than this. However, if you go to very large scale, and then you only need to sell the carbon at $1.69 minimum selling price in order to break even, which is really good. So you have to build a large micro pyrolysis plant in order to sell the carbon. Minimum selling price of carbon is $1.69. So this price already close to carbon black. So that means for such advanced carbon we produce from this process, we can, if we sell at the carbon black price, we can just to make money. So anyway, this is the economic outcome of the TEA analysis. Anybody has any questions? If you have any question, I can go through detail. Otherwise, it's gonna take me another hour to interpret this economic data. But I want to know, I want to show you the conclusion. Do you have any questions on the techno economic analysis? The idea here is that we want to remember, we want to sell the carbon to offset the loss, all right? So remember here, keep remembering here. So methane pyrolysis, you produce 2 hydrogen, and then methane steam reforming, you produce 4 hydrogen. If we put the environmental impact filter on the side, don't worry about it. So the driving force here is from economic standpoint of view, how do you offset or compensate loss of the yield? You agreed, all right, sell the carbon. So this is the reason we have done this the economic analysis. We want to make sure how much carbon we can sell in order to make money. Make sense?
Yes,
anybody
sir.
has any question? Good?
Sir, from that
Yeah.
second process is there, sir, from water we are producing hydrogen. Hello?
Could you repeat your question? Please speak very slowly. Your microphone has some problem. I cannot hear you. I cannot hear clearly. Speak very slowly. Go ahead. Repeat again.
Water we are using to produce hydrogen, no, sir.
The water used to produce hydrogen. What's the question? You said
water. Methane plus water we are using to produce an hydrogen, no, sir.
Yeah.
But in that case, we are getting carbon dioxide, no, sir.
Yeah. So
that carbon dioxide we can separate and we can produce oxygen and carbon, no, sir. How, like methane, we are separating carbon and hydrogen.
over here. Yes, steam reforming. You need the water. What's the problem with water? I think the end result here, if yes, you use water, but 2 hydrogen coming from water, but the end result is one. There's no cost on the water. Okay, water is free. The cost is the methane. Methane you pay the price, and here methane pay price. So basically, economic, how much is the price you pay from feedstock? Equal, all right? One more. And how much product get? 4 hydrogen, 2 hydrogen. Water is not in the equation. You have to assume water is free. You follow me? So that's why if you lose the hydrogen, you have to compensate. How you compensate this carbon? It's going to be you compensate that to allow loss of hydrogen. So I do not understand your question about the water. Why water is in the picture? Can you rephrase your question again? Why you believe water is a problem? Why do you believe water is a problem? Can you say it again?
Maybe don't know, sir.
Hmm?
That water problem will be in future.
So you are talking about the water scarcity, all right? So that means if you run this method steam reforming, you are basically going to be running the problem of the clean water problem. That's what you are saying, all right? So
Yes,
that means in the future water will not be free. Is that correct?
yes, sir.
Yeah. So okay, that's a good question. Yeah, if you run the method steam reforming, true, in a certain part of the world, the sooner or later water will be the problem. But it's not going to be a problem. What are you going to use for hydrogen? If you combust hydrogen, will water coming back? Some hydrogen will be combusted, all right? Because so water will be coming back, all right? True. If you there's because of water, clean water, because you have to do the membrane treatment, but the water will be recycled. So if you look at this in a global point of view, if unless you don't combust hydrogen, what do you use hydrogen? So because you have to use hydrogen generate power. Today power is generated by methane combustion, but in the future you may have to combust hydrogen, or even you run the fuel cell, hydrogen fuel cell, the water will come back. Yeah. So anyway, so I think yeah, I mean it's a good question. Yeah, you may run into water problem, in certain time window, but in the long run, this water should be balanced. Make sense? Yeah. Okay. So let's take a look at this problem from the different angle. Okay. So this is very complicated process flow diagram. Again, when you do technical economic analysis, you need to have a different scenario. Base case, which is commercially how you produce the hydrogen from the natural gas, and then you have the B and C, the two different cases. Anybody has any question, or you just talk something else? Is that question? No question. All right. Okay.
Yes.
So I think if you talk of something else and not related to these courses, please move away from microphone, because the moment I hear microphone, I thought you have a question. Okay. So you on the side, please move away from the microphone, because your microphone has some kind of feedback. First, I cannot hear clearly, and second, if someone that talk something not related to these courses, and that microphone pick up the very sensitive. Okay, so the base case, there's a base grown case. I will interpret the base grown. Base grown case means it's a different way to grow the carbon nanotube. Then there's a zero CO2 emission, which I'm going to spend time on it. What is a zero CO2 emission case? There's a true zero CO2 emission. Okay, let's go back to this direction. So we use the renewable power to drive this direction. Okay, and then the objective here is to produce hydrogen and advance the carbon. And true, renewable power sometimes is expensive. There are two ways to drive the direction. It's nothing but heat. One is we continue to use the microwave to sustain the heat into it. But keep in mind, there's hydrogen produced. Part of hydrogen can be used to sustain heat combustion, because burning hydrogen is not going to cause a problem because you generate water. Is that right? So now we create another scenario, which means the process is partially heated by the microwave, and also the partially heated by the hydrogen. See this PSA? PSA separate hydrogen, and then some hydrogen is sold to market. We do produce hydrogen, but part of hydrogen is recycled to the micro pyrolyzer. and then together with the microwave. So this is the way you balance electricity or renewable electricity, and then to see. So let's say if you can sell hydrogen at a good price than electricity, you don't need a PSA. You just sell the hydrogen. However, if you process, the saying that, hey, my hydrogen in the market, green hydrogen is not that much, and then not the green hydrogen, carbon neutral hydrogen, but I want to save renewable power, then you can recycle part of it. So this is a strategy you can use in any economic analysis, and that will guide you the commercial plan. So regardless, with the PSA, pressure swing the adsorption, you have flexibility either to sell the whole hydrogen or part of hydrogen recycled. So this is so-called zero CO2 emission approach. We do not use the natural gas combustion to sustain the reaction. We use renewable power. We also use the part of hydrogen combustion. You understand the? Do you understand that this is the flow diagram here? I don't know if let me enlarge a little bit so you can. Oh, okay, so probably this is a better way to look at it. So this process flow diagram. I think if you are working as a system engineer, you should be familiar with this block flow diagram. So this methane pyrolysis produce hydrogen, and then we can use the PSA to separate a part of hydrogen and then recycle them, or we can sell the whole hydrogen and then without running the PSA. And then the reactor can be driven by microwave or can be driven by the sum of hydrogen. Okay, so this process is called zero emission, purely zero emission CO2, because we do not have any fossil combustion to sustain the heat. And also some of hydrogen go into the catalytic regeneration, because all of the catalytic regeneration you need the temperature, all right? You need to maintain temperature. Traditionally, that temperature is maintained by the natural gas combustion fire heater. So some of hydrogen you can see and supply as heat. So the entire process, we use some of hydrogen produced to sustain heat, reactor, and then downstream separation regeneration. Okay. Anybody has just asked question? Go ahead. What's the question?
Catalyst regeneration. In the catalyst regeneration, how do we how it is regenerated? That is, whether we have to reuse the catalyst or the catalyst again regenerated. I think there is a difference between catalyst.
Thank you.
Reuse and
very good. Okay, very good. Okay, let me show you how the catalyst regenerate. Yeah, this is reason catalyst regeneration. Okay, so this really relate to the catalyst regeneration. So basically this cartoon really tell you what is the catalyst put in the reactor. Okay, the catalyst begin with. Let me write it down. Okay. Very good question. I really like you guys asking questions so I can interpret it. Otherwise, I don't have time to interpret it. So catalyst, I need to find something. I'm going to come back to this. Okay. So let me have a new. So basically, catalyst begins with a CNT as a support. And nickel, copper are anchored onto the support. Okay. So this is how we make catalyst. First, we use the CNT as a support. Then we have nickel and copper, which is the active site. Okay. Okay. So once you have this is the caterpillar, I try to draw a cartoon in here. So let me go back here. So this is catalyst. We begin with the carbon nanotube. Do you see that? Then we put a metal. You see the metal? The red dot on metal on the surface. And that's a cutoff. So we put this catalyst into the reactor and then begin the process. And carbon nanotube grow on this red dot. Okay. So at the end, so at the end of the methane pyrolysis, keep in mind we begin with the CNT, and new CNTs are produced on the this center. All right. So what does it mean? There's the beginning CNT is called seed, and also new CNT. They are the same. So we need to harvest metal. Again. Okay, so I want to give you some data. Okay, so let's say we begin. It's very This cartoon is very difficult to understand. So I'm going to talk about this cartoon. Okay, so basically I'm going to say we begin with 1 gram CNT. Okay, and then 1 gram nickel and copper. Okay. After reaction, 2 gram CNT is produced, and 1 gram remain. All right, 1 gram nickel copper remain. All right, make sense? So I begin with 1 gram CNT, 1 gram nickel. This is my catalyst. After reaction, 2 gram CNT is produced, and the 1 gram nickel still in there. All right. So the mixture altogether, I'm basically. So if you look at this mixture, so I begin. This actually the totally 3 gram of the CNT and 1 gram nickel copper. Keep in mind, come back to the reactor. I only need 1 gram CNT and 1 gram nickel copper. All right. So that means 2 gram need to be gone. All right. So 2 gram is product, and then it's basically I need 1 gram. 1 gram CNT plus 1 gram nickel copper. All right. So 1 gram CNT, 1 gram carbon go into the reactor. But at this point, I want to show you the mass balance. Okay. Make sense? So basically, I begin with a 1 gram CNT and 1 gram nickel copper, and then go into reactor and then react with the methane. So methane turned into the CNT. I produce additional 2 gram CNT, but the 1 gram nickel copper is still in there. All right. So basically, at this point, I have a mixture of 3 gram CNT and 1 gram of nickel copper. And then keep in mind, I need to separate. I need to recover metal. Nickel copper is very important. I need to recover and then have them go back with another 1 gram CNT. But I want to not reject, and then produce 2 gram of the CNT as a product. Is that correct? So what does it mean? I mean this cycle has to go around. So beginning 1 gram, CNT, 1 gram nickel copper. Under 3 gram, I need to separate them. To separate a solid catalyst with a solid carbon, there's a technique called acid treatment. Okay, so people work in the field of carbon nanotube. You know, carbon nanotube will not be dissolved in acid, but the metal does. So you can use the strong acid to dissolve the metal, and then the metal will be continued, and then the carbon nanotube will be purified, and then it goes through the cycle. So do you understand? I hope everyone understands that this is the mass balance. I am beginning with 1 gram CNT, 1 gram nickel. That's what I need going in reactor. After reaction, because the methane react, I end up with 3 gram CNT, 1 gram nickel copper. I need to use the acid wash to separate this nickel copper so that I can harvest 2 gram of CNT. If I do not do the acid wash, this CNT will not come out because there's metal in there. I recover metal, this metal can go back, beginning the second cycle. I'm going to stop here. I want to make sure you understand. Do you understand this mass balance?
Yes, sir. We understand it, sir.
Okay. So this is how we
understand, sir.
All right, cool. That's very good. So this is how. Just before you ask me the next question, this is how we. Where's my cartoon? So now we come back to here. Your question is how we do catalytic regeneration. This block, which is the number A310, and then how we regenerate it is this process. Okay. So what's the next question?
Sir, what about the purity? When we add 1 gram, we get 2 grams, so that is the extra 2 grams we are getting. Will that purity will be equivalent to the purity of the first carbon nanotubes which we have added?
Very good question. Depend on which market you are going to sell. Okay, so if you sell, keep in mind that different market. If you sell the carbon into this market, the purity should be very high. That means essentially need to be metal free. So that means you have to do acid wash again. Now, if you sell into this market, carbon composite, it's okay because electronic conductivity is not the problem. It's not the issue here because here we want to use the crystalline structure, and then you build basically this is a building block. While we are speaking, Toyota is trying to change their plastic interior with the carbon composite. Actually, some for the Toyota truck, they already built in there. They are pretty strong. In this case, if you have a small amount of the metal left over, nobody cares because you are using the mechanical property of the carbon material. But here you use the electronic, then you have to be metal free. Did I answer your question? That means this acid wash is very important. It's all dictated this purity. If you don't wash it, number one, you lose the nickel copper. That's very bad. If you and also you cannot sell in the carbon nanotube because you have nickel copper ended in the carbon. So this acid wash, how thorough or how clean you wash it, is very important. Very good question. Next, what's the next question?
So that's all. One more question.
No question.
How many times you can use this catalyst?
How many catalysts used in the reaction? All right.
How many times we can use acid wash for the catalyst?
Oh, you can do forever acid wash, because the thing is you have to do the acid wash and then carbon recovery, and then the only thing is you have to treat acid. Do you see that acid is is nitric acid? Nitric acid we have to basically the recovery. So there's a cat regeneration. Excuse me. In the process, there's a because after the metal wash, the strength of the nitric acid diminishes. All right, then we had to rebuild the nitric acid. See the nitric acid recovery. So you have to reoxidize it and build the nitric, and then it will be continued to use. So the acid wash is very effective. It just depends on how much you use. It's just either you buy or you can recover it. And then so how you recover nitric acid? You basically there's a process. You use air oxidized NOx, and then you have water come in, then you rebuild it. And then if you are short of nitric acid, you can come in. So to answer your question, acid wash you can wash the many times you need. So the guideline will be what's the level of metal you need. Do you want the 0.1% of metal or the ppm level? So then you wash multiple times in there. In the laboratory, we just wash 3 times. We can get metal free. But in the industry, it just depends on how efficient you process. And by the way, that process needs heat, because it's not just the wash. You need to dissolve. So that's why the hydrogen come into this the regeneration, and also you have to heat the process and to make sure it's effectively dissolve the metal. Yeah. Okay.
Thanks, sir.
Any other questions?
No, sir.
All right. So until this point, you may be wondering, hey, Dr. Hu, why are you, remember this project is a $3 million. I lead a team. So this team consists of the 2 universities, 1 small company, and then 2 the large company. SoCal Gas, Southern California Gas is a very large company. So you may be wondering where we are on this project, how big a unit. That's the next I'm gonna. So I think we still have probably 20 minutes to show you, and then we finish today. Okay. So this is a pilot plant build. Do you see this guy? This is the student sitting here. This is a pilot plant. This is the microwave, the reactor, which is the glowing in here. And then in this case, we use both microwave and also microwave plasma. Okay, because you need to pre-active the methane, and in order to do the pyrolysis. And then this is the reactor. Because it's a continuous flow, the reactor, we have to use the so-called fluidized bioreactor. If you're familiar with the petroleum refining industry, a lot of reactor is fluidized. Fluidized means it's there's no pressure drop and easy to handle. Okay, so then oh, I show you this already. Activation energy. So this is the size of the reactor. Remember I mentioned it's modular, all right? Modular, we produce the clean hydrogen, and then we put it in a container. So this is really, you probably see this container everywhere around the world. We put in the container, so we can put it on a truck and drive on the side. This is where we are. And then I want to show you the cartoon how we build a container. So this is the container we have, and then we build inside, and then so the size, the throughput or the flow rate today is 50 to 200 cubic feet per hour. It's very far. It's very far for flow rate. Flow rate direction. We did this demonstration at a different the gas well, the different place. So it's a lot of work in there. And then in what we put in the trailer today is like this big. So I don't know if you can see the size, how tall this is the reactor. This reactor actually just fit in here. Did you see that? The reactor fit in the trailer. It's pretty much it's taller than a human being in there. It's a methane pyrolysis, microwave driven the pyrolysis reactor. We put in a trailer and drive in the field. Okay, so I'm gonna show you the cartoon So plasma jet. This is a field, the gas field. We park this, and then we basically, I think we did like a 3 months demonstration, make sure we produce the decent amount of the carbon. You see how we unload using crane to unload the pilot plant trailer, put in the field, and then do the reaction. So let me show you the cartoon, the plasma jet. Listen, I will come back to here. Yeah, see this? So you can see the methane, and you see that the blue line, the blue thing, that's methane. Nitrogen, I can tell if you work in the microwave plasma field, nitrogen is a pink color, and the pink or the purple color, and then this is light blue, and if you see that's methane. So this is really the methane plasma, and then we flow onto the downstream that's catalyst, and then they produce the carbon nanomaterial and hydrogen. Okay, so back to here. So the heating rate. Remember the microwave. The heating rate is very high. I think the transfer rate is the 10,000 the Kelvin per second. So this is the reason you see compared to conventional, why microwave can handle so much of the gas. I mean, this tell you. I mean, this is really the pilot demonstration. We actually calculate and also measure the heat transfer rate. How important the heat transfer rate? If you recall this graph, and then no matter how you change the flow rate, which means how much feed you push through, conversion essentially doesn't change because actually this is equilibrium conversion, and then they basically the heat transfer so fast. However, if you use conventional heating, because you heat transfer rate is so slow, and then when you increase the flow rate, from 30 SCCM to 120, your conversion decrease, moving away from equilibrium curve. Okay, so this is all largely because of the high heat transfer rate. So look at the heat transfer rate. It's a 10,000 Kelvin per second heating rate. So anyway, it's rapid direct energy input. Direct energy input means the heat transfer is not from the external. It's going directed inside, and also the industrial robotics is really modular. Okay. So I think that before we end today, I'm going to show you. You may be wondering where we are. We already demonstrated in the shale gas field. I'm going to show you another technique we are doing on working on the shale gas. There are 2 more slides to go, but I want to ask a question. If anybody has any questions?
Okay.
No question? Okay. All right. So I'm going to show you, since you are not familiar with the shale gas, I'm going to show you quickly about how the shale gas drilling. Then I will tell you, this is more like a subsurface hydrogen production. We build a pilot plant, here, the modular. You understand that, right? But we can also produce hydrogen from the subsurface without building anything on the ground. So that's called the subsurface hydrogen production, largely because we can drill and also introduce microwave in on the underground and produce hydrogen. Okay, so I think we have probably 10 to 15 minutes. Give me some time. I will show you how the shale gas drilling is taking place and how we put the microwave to the underground. This is the trend of the future. That means you don't have any equipment on the surface, on the ground. Hold on, okay. This is gonna be 3 minutes video, okay? Hold on, I'm gonna share this video. Hold on. Okay, so I'm gonna share this video with you. I'm gonna share this video so you understand the shale gas. Can you see this video? Anybody can tell me? Did I share this video? Can you see it?
Yes, sir.
You can see it, right? Okay, this video is 3 minutes. Okay, just watch it. I'm gonna go from beginning. Okay, so hold on. What is shale gas?
Pressurizing the steam water. Yes.
Do you see that? That's a shale gas. All right. So yeah. So now you know the shale gas, the drilling, and then how we come up the shale gas. And let me come back here. This is the reason. So this is the reason that so many drilling sites. Did you see that decommissioning? That means when the lifespan life of the well which is depleted, you had to move all equipment to the next. That's why the modular production, which is the cartoon shows here. It's so important. You have to be modular. Otherwise, you cannot, you basically, if you build a gigantic, a huge plan, it's not going to be helpful. So you have to have modular, keep on moving. Make sense? You understand the shale gas drilling and fracking, and then the why is need to be the modular, is that right? Because the production unit cannot sustain a huge plan. So and also there's life of each well. So you finish, you keep on moving. Then you have to seal a decommissioned well and then put it back in the original. So that's why the shale gas is different from the traditional natural gas. Traditional natural gas you can produce a lot, but shale gas is very difficult because each drilling you can only pump this much of the gas, maybe in 2 years, some even in 3 months, some even in maybe 7 years. But whatever you down, your modular has to keep on moving. Make sense?
Yes, sir.
Okay. So before end of today, now you see the drilling. This reason I show you the video in the future. So today we build this the modular, the next to the unit. Okay, we produce hydrogen and carbon. I'm asking you a question. So, what if the carbon is oversupplied? That means there's too much carbon, and then nobody need it. But I still need hydrogen because the hydrogen will sustain our daily life. You can combust hydrogen. So let me make a point. What if you only want hydrogen? They say no. You say I don't want carbon. Doesn't matter the carbon nanotube or something. And then I just all I care is about hydrogen. So that's what I'm talking about. Okay, all you care about hydrogen, you leave carbon behind. There's a technique you can do. You see the drilling, all right? You can drill vertically, horizontally, all right? We can have a methane pyrolysis on the underground. So basically, you introduce a so-called microwave onto the ground, and then there's in the shale gas. You can still drill, but do not pump the shale gas. But we do the methane pyrolysis here, and gas coming out, and we leave carbon behind. So all those carbon will be stay in there. Doesn't matter it's a carbon nanotube, carbon black. I don't want it. I just want hydrogen come to the surface. It's called underground methane pyrolysis. Underground coal gasification has been done. I'm pretty sure in India you heard about underground coal gasification, but this underground shale gas pyrolysis, we leave carbon behind and we have hydrogen come out. Any question here before I show you? We did a simulation. We basically, but in order to enable the underground pyrolysis, you have to make sure the rock has a catalytic function, all right? And also they are sensitive to this microwave we introduced to the underground. Two things has to happen. First, we should introduce a microwave to underground. That has been done. Yes, you can do that. Microwave can be introduced to underground. Second, the rock, which is going to be catalyst, need to be sensitive to microwave, so they can under microwave, the irradiation. So those rocks become catalyst. They can basically react with the methane in the shale rock. So we did simulation. We took the rock from the drilling and then come to our laboratory and we do testing. They are active. So basically, those rock. So this is the condition. So those are the rock, the shale rock, and then we basically take to lab. We simulate underground condition, but we use a microwave to drive the direction. You can tell. So each rock, they have a basic activity. Okay. So this is a trend of the future. That means instead of doing the surface, the pyrolysis, produce hydrogen, we go underground. We only need hydrogen, leaving carbon behind. So that means carbon doesn't matter. Carbon nanotube, carbon, they are permanently sequestered underground. So all because of this drilling become available. So you can drill available. We can install microwave in the same location along with the drilling. I think I'm going to end today here. Any questions?
No, sir.
Okay, so this is the future trend. So tomorrow is the last day. I'm going to let me see the topic tomorrow. Okay, tomorrow there are 2 sessions. Okay, hold on. I need to look at the lecture I prepared for tomorrow, because sometimes I change something, because there's one topic I didn't cover. It's called AI machine learning. I don't think this class is good to discuss AI machine learning. I only have one publication, AI machine learning, and then it's too complicated. So I changed that only topic I changed. So tomorrow, let me tell you what I'm going to talk.
The question.
Hold on, I'm going to tell you the topic I have, okay?
Sir, no doubts.
It's a future, it's called the future trend in sustainable ammonia production. So that's okay, then I'm going to stop sharing. I'm going to share it. I already prepared this. Okay, so tomorrow we are going to about the future trend in sustainable ammonia production. Okay, so it's all related to hydrogen, how you produce. There'll be solid oxide fuel cell, and also the ammonia cracking, and then all kinds of things. That'll be tomorrow. But tomorrow there'll be 2 sessions. One session we are going to talk about the future trend of ammonia. The other I'm going to discuss about as a bonus. I'm going to talk about something, try to introduce another area we are doing the research on, which is where is my slide?
No,
So you just okay. Tomorrow there'll be 2 topics. Okay, one is the future trend of ammonia production. The other is I cannot find my slides here. I open my slides and it disappear. Hold on. Give me 1 second, okay? Okay. Another topic, if I have time, I'm going to have microwave catalytic upcycling of single-use plastic. Plastic recycle is a big problem, but plastic upcycling. So basically, we turn waste plastic into hydrogen, and of course, that hydrogen can be used for ammonia. And also, we also turn the waste plastic, because single-use plastic, into the monomers and hydrogen. So I'm going to talk about those. It's related to the hydrogen production, because you can turn plastic into hydrogen and carbon. It's the same as the methane pyrolysis. You can pyrolyze methane into hydrogen carbon nanotube. We also pyrolyze the plastic in hydrogen carbon nanotube. In the meantime, we also turn the plastic into olefin and hydrogen. Okay, so tomorrow will be 2 topics. Okay, the future trend, and also the it's called upcycling of single-use plastic. Okay, there'll be 2 sessions. Yeah. Okay. Any questions? We can talk. If you have any questions, we can talk tomorrow. I think today we are run out of time. So, okay, see you tomorrow.
Thank you, sir. Thank you for the presentation, sir. We'll be back today tomorrow.